In the empty blackness of space, surrounded by hostile planets and freezing vacuum, planet Earth is an oasis of life. And all because of our protective cocoon of gas. This blanket of air shapes everything we see on Earth. It protects, insulates, and sustains us. It carries water around the globe and shields us from cosmic impacts and killer radiation. It's time to uncover the invisible wonder that is our atmosphere. Down here on the Earth, we rarely give much thought to our atmosphere. Because we can't see, smell, taste, or hear it, we take it for granted. But our air is all that stands between us and the vacuum of space.
We've got this canopy that provides us a lot more than just an atmosphere to breathe in. It definitely shields us.
The atmosphere is divided into 5 distinctive layers: the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Each layer is less dense than the one below, stretching miles above our heads.
How far out it goes is depending on which scientist you talk to. Some say it ends at 300 miles, some say it extends out to Mars.
We live in the layer closest to the ground. Here in the troposphere, the air is thickest and the pressure greatest. Our bodies are perfectly matched to these conditions.
Our chemistry, our very nature, our metabolism is completely shaped by the atmosphere.
To appreciate our atmosphere, we'll rise through its layers, traveling from the planet's surface, miles up above the mountains and the clouds, to the very edge of space. August 16th, 1960. One man is preparing for a record-breaking journey into the mysterious skies above. To a lethal world above 99% of the Earth's air, where an unprotected human would die in seconds. Where the temperatures plunge to 67 below, and the air pressure is 1/100th of that at the surface. Colonel Joseph Kittinger will travel almost 20 miles high. And then he will jump. This is a key military mission, one of the first steps in the space race. Kittinger will be testing the human body's resistance to high altitude, low pressure, and rapid free fall. He will be trialing new technology he hopes will protect him.
It had never been done before, but we were not there to set a record. We were there to gather information that we needed for our space program and for our high-flying aviators.
Ground crew prepares his vehicle, a helium balloon, and a rudimentary open-sided gondola.
Just an open gondola. It was designed just to carry me up there. It was a space platform, an elevator, I called it.
At 5:30, Kittinger's preparations are over. He boards the gondola.
My crew chief said, "Are you ready?" I said, "I'm ready, let's go." It was a very smooth takeoff, and I started ascending. Up, up, up.
30 minutes after takeoff, Kittinger reaches 29,000 feet, the middle of the troposphere. At this altitude, the air is so thin that each breath contains only 1/3 of the oxygen found at sea level. Kittinger breathes from gas bottles connected to his sealed helmet. He's still barely 1/3 of the way to the jump point. There are another 14 miles to go, and the air pressure is dropping rapidly.
So at about 40,000 feet, suddenly the pressure suit starts inflating, and that's when you start checking it to make certain that it's working properly.
But there is a crucial fault in the suit. The glove covering his right hand is not sealed.
I had an option to tell the ground that I had the problem, And I knew that if I did, they'd probably make me abort the flight. And I was concerned that if we had to abort that flight, that we would have been turned down to try to do it again. So I didn't tell them.
Kittinger prays that this is an isolated fault and continues to climb at 1,000 feet per minute. After 89 minutes, he approaches his target altitude. The balloon's climb slows and then stalls. Kittinger is in the mid-stratosphere, a record 102,800 feet high. At this altitude, he is 3 times higher than the tallest mountain. Despite the pain from his bloated right hand, Kittinger can still glimpse the wonder around him.
I was not there as a poet. I was not there as a philosopher. I was there as an engineer. But it was very beautiful. All of a sudden, looking up, the sky is no longer blue. The sky is black. It was a phenomenal perch, standing on the doorsteps of space, looking out.
No man has been here before. Without his protective gear, Kittinger would be dead in seconds. And it is now time to make the long... Kittinger would be dead in seconds. And it is now time to make the long...
Think back toward a more friendly environment, a friendly planet that we're used to. I had made this jump 1,000 times in my mind. I'd gone through every step 1,000 times. Well, just before I jumped, I said a silent prayer. I reached over and hit a button that started the cameras going. And then I just did a little hop off the step of the gondola. You can't tell that you're going fast, you can't tell anything. And I looked up at the balloon, and the balloon was firing into space. And I said, gosh, that's amazing. And then I realized it was me that was going down at a fantastic rate, and the balloon was standing still.
He falls for 16 miles. The thin air offers almost no resistance. He reaches 614 miles an hour, approaching the speed of sound. After a record-breaking 4 minutes and 36 seconds of freefall, Kittinger opens the main parachute. He drifts down to the desert floor and lands.
We were just elated because we had accomplished what we set out to do. There was a lot of people who said we couldn't do it, and we proved that we could do it.
The mission has been a stunning success. Kittinger's skydiving record stands to this day. He takes his first deep breath of air with a newfound appreciation for our atmosphere.
It was a relief to be back on the planet Earth that we love so much. A planet that has an atmosphere that we can live daily.
Kittinger forged a dizzying path through the atmosphere. Our journey begins just a few feet off the ground with the air we breathe. We take for granted Earth's blend of gases, the perfect mix for heat and energy. And astronomer David Grinspoon believes we'd be hard-pressed to find its equal anywhere.
The more we learn about planets, the more we learn that they're all individuals. They're like people in that sense. So as far as what we know now, Earth's atmosphere is completely unique.
In the past century, telescopes and space probes have uncovered the extreme atmospheres of our neighboring planets. A journey across our solar system reveals exactly how unusual Earth is. Clouds of near-frozen gas flow over the icy surfaces of Uranus and Neptune, while the sun has blasted away the atmospheres of Mars and Mercury.
To me, it seems as though Mercury doesn't have an atmosphere at all. In fact, if you were on the surface of Mercury, it would look to you as if you were out in outer space.
In contrast, Jupiter and Saturn are all atmosphere.
Unlike Earth, Jupiter doesn't really have a solid surface that you could stand on and then have your head up in the atmosphere looking at the clouds. It's just a giant gas ball.
Only one other planet shares the Earth's thick atmosphere and rocky surface: our near neighbor, Venus. But even here, there are striking differences. Dr. David Crisp has spent 20 years studying Venus's acrid air.
Imagine you're at the surface of the planet Venus. You're at pressures that are high enough to crush a nuclear submarine. The pressures there are about 90 times the pressure of the Earth's surface.
This pressure is combined with extreme heat, 900 degrees Fahrenheit, hot enough to melt lead. Clouds drift over the baked surface, but they are not water vapor. Venus's clouds are made of concentrated sulfuric acid. Venus is a stark example of how extreme an atmosphere can be. But the real mystery isn't why Venus is so hostile, but why Earth hasn't followed the same path.
As planets go, Earth and Venus are essentially twins. They're almost exactly the same size. They're also very close together in the solar system. In spite of that, their environments evolved in dramatically different ways.
To discover why these twin planets followed separate paths, and to explore what gave us our precious atmosphere, we have to travel back. Back 4.5 billion years to the birth of the solar system itself. The birth of the solar system created Earth's earliest atmosphere. Huge quantities of material orbiting the sun fused together into protoplanets. Jupiter and Saturn formed into gassy spheres. But on Earth, most of the material condensed into a molten core. The remaining gases bubbled forth from the liquid rock, forming the first atmosphere. Our planet's gravity stopped these gases from drifting off into space. But Earth now had to face the ravages of the solar wind, a stream of charged particles thrown out by the sun. This same wind had a catastrophic effect on Mars. It has stripped the air from the planet's surface, blasting it deep into space. The red planet's atmosphere is now only 1/100th as thick as Earth's. Our planet was spared this fate. The magnetic field generated by the Earth's core blocked the solar wind, preventing it from blasting away the fragile air. But the Earth's atmosphere was still very different from the one we breathe today. It contained high levels of carbon dioxide, a gas with a key ability to absorb and hold on to heat. Carbon dioxide still makes up 95% of Venus's atmosphere. It superheated our twin planet to the point where its water boiled away into space. And yet, this didn't happen on Earth. David Crisp believes that was down to a chance event.
If Earth kept all of its initial atmosphere, it probably would have turned out a lot more like Venus. But that didn't happen. We were the victims of a very lucky accident.
Earth's big break came 4.5 billion years ago. Back then, the solar system wasn't limited to the 8 planets it has today. Instead, a swarm of protoplanets, or planetesimals, orbited the sun like bees around a honeypot. One Mars-sized body was heading straight for Earth. In a colossal cosmic collision, it slammed into our planet, creating our moon, and according to Crisp, removing the atmosphere that still blights Venus.
Okay, the tennis ball on the string represents the early Earth during the accretion phase of the solar system, just before the moon-forming impact. And what I'm going to do now is to accrete a little bit of the atmosphere onto the top of the ball. A little later on, an object about the size of Mars passes a little bit too close by, and there's a collision which removes a large amount of the material that is accreted onto the Earth. Most of it that made up the atmosphere is just gone.
This ancient event was the defining moment for our atmosphere. With the original deadly gas mix blasted away, our planet's air could slowly evolve into what it is today.
We were left with this atmosphere made of molten rock and vaporous rock. It took millions of years for that atmosphere to fall out and to be replaced by an atmosphere made up of nitrogen and carbon dioxide and water vapor.
These new gases came from above and below. Volcanic eruptions spewed out fresh stalks of nitrogen and carbon dioxide from within the planet's molten core. While the vital element of water may have been delivered by icy comets, each impact bringing a new supply of frozen liquid. But the air still lacked one of its key ingredients.
One of the things that was missing is free oxygen, molecular oxygen, O2, the stuff we breathe.
Dr. Janet Seifert of Rice University in Texas searches for the event that produced the atmosphere's final element.
We know from the rock record that for the first half of Earth's life, there was no oxygen in the atmosphere whatsoever. There were greenhouse gases like methane and CO2, but there was no oxygen.
But the rock record shows a sudden change, dated to around 2.5 billion years ago. Evidence of the first oxygen in the atmosphere. The gas was released by a humble microscopic living organism called cyanobacteria.
Well, it turns out cyanobacteria are the only things that can actually produce oxygen. So we know that at some point cyanobacteria colonized enough of the planet in order to produce enough oxygen that it became resident in the atmosphere.
The microbes that produce the oxygen are distant ancestors of modern bacteria. Bacteria that Seifert finds living in the barren primeval landscape of Cuatro Ciénegas, northern Mexico. Over 3 billion years ago, they experienced a sudden genetic shift.
They discovered something that no other group of organisms on the planet has ever discovered. They've learned how to do oxygenic photosynthesis. They take sunlight and CO2 and use the energy of the sunlight to split water and make oxygen. And that's so important for us today because oxygen is what we breathe in. It's what made a difference to our planet that's not like any other planet in our solar system.
As the microbes multiplied and spread, the gas built up in the air, transforming the planet in a process known as the Great Oxidation Event.
Oxygen is very powerful. The world gets turned upside down. Everything has to begin to adapt to now a completely new atmosphere where oxygen is dominating.
First, the oxygen reacted with the oceans, causing iron within them to form rusty deposits on the sea floor. Then its effects reached dry land. It reacted with soil and rock, giving them a reddish, rusty tinge. And once these minerals had absorbed their fill of oxygen, the gas began to gather in the atmosphere, with dramatic consequences for life.
Complex animals could have much higher metabolisms because of the sheer potential that oxygen provided for them, and a whole different kind of evolution was able to take place.
Powered by oxygen, life evolved from single-celled organisms to complex animals. And plants also began releasing oxygen, thanks to an ancient adoption of photosynthesis.
A very ancestral, primitive plant cell either engulfed or tried to digest or surrounded a cyanobacterium. And instead of digesting it, it actually became an organ within the plant. So every bit of the oxygen, even if it's coming from a plant that you see in your yard, is coming from an ancestor of a cyanobacteria resident inside the plant.
With the rise of oxygen, the air's unique blend of gases was complete. It joined the nitrogen that plants need to grow, the methane we burn, the argon that lights up Las Vegas, and the carbon dioxide we use to fight flames. This air we breathe has changed planet Earth, molding its terrain and habitats. And as we continue our upward journey, we run into another vital substance: water. The turbulent movement of our atmosphere carries water vapor around the globe. Powerful winds and violent storms smash our buildings and drown our fields. But without them, the land would be bone dry. Our atmosphere is in constant motion. The moving air that causes our weather circulates between the ground and 50,000 feet. It is the sun that drives this movement. When solar energy reaches Earth, it heats the surface and atmosphere, but it does so unevenly. This temperature difference causes the air to move. Hot air near the equator expands and rises. Cold air at the poles becomes denser and sinks. NOAA's Marty Ralph can track its movement over the globe on the revolutionary Science on a Sphere simulator.
What we're seeing here is a portrayal of the Earth's surface temperature. And red and warm colors are warm temperatures like we see in the tropics here. Up in the poles, you see the blues and the greens. Those are the colder surface temperatures. So we can watch this and actually see the warm air moving northward, the cold air moving southward, and we can see the changes in the seasons.
If the atmosphere didn't move, the poles would be 45 degrees cooler and the equator 25 degrees warmer. The great deserts of the Sahara, Atacama, and Mojave would expand dramatically. Northerly cities like London or Boston would be locked in an icy winter. It is only the atmosphere's circulation that prevents this. It regulates the temperature, moving the air to create the weather that covers our globe. The planet's rotation twists the air as it flows, helping form the hurricanes that lash the coasts. As moist air wells upwards, clouds become electrically charged and send lightning bolts crashing down to Earth, superheating the air to 18,000 degrees. And as the air cools, water vapor condenses into clouds and rain. This water evaporates from the world's oceans. At any moment, 0.001% of the world's water is being carried in the air. But that tiny percentage adds up to almost 3,000 cubic miles of liquid. If the air didn't carry water, the land would be bone dry.
Storms do a really important job for the atmosphere. They help reduce the difference in temperature between the poles and the equators. And in the process, they actually create the rain and snow that we depend on.
One of the most powerful weather systems is a newly discovered set of water channels running through the air. Ralph's current research focuses on these mysterious rivers in the sky.
One of the phenomena that really influences where the water is available for us are these regions where water vapor transport is focused. We've come to recognize that phenomena as an atmospheric river.
Atmospheric rivers are narrow channels of hurricane-force winds that can stretch for thousands of miles. A single river can carry 3 times as much water as the entire Mississippi. They provide almost half the annual rainfall for parts of the American Pacific coast. But when they remain over one area for a day or more, they can produce violent flooding.
Heavy winds, lots of water vapor, a storm track that's not moving fast adds up to a big flood event.
The rivers were only recently discovered because they form over the world's oceans. We still don't have enough data to forecast their floods.
An example of the challenges we face in weather prediction is that while this model can actually produce an atmospheric river, like we're seeing right here, a week ago today we looked at the forecast for today, and it said there should be a strong atmospheric river creating heavy rain in Northern California. Well, instead, it's hitting Canada. That's a huge difference.
To fill the gap in data, Ralph explores the rivers on research flights. The rivers form in front of banks of cold air. They create channels of wind that carry huge quantities of water vapor from the ocean to the coast at up to 100 miles an hour.
These are like conveyor belts for water vapor. They're very narrow, and yet they do 90% of the water vapor transport for the global atmosphere at those latitudes.
When the airflow hits a mountain, it rises up, shedding its water as rain and snow. Ralph has tracked how the rivers move with the changing seasons. But to fully forecast the floods, he needs a lot more atmospheric data. He believes robotic drone aircraft, developed for the military, could continually measure the air over the oceans, charting its temperature, winds, and humidity. And the flights could also track how the rivers are changing.
We're starting to see evidence that the more intense atmospheric rivers might become more frequent in certain parts of the world, and that will contribute to increasing the frequency of flooding.
The changes Ralph has identified are part of a wholesale shift in our climate and atmosphere. Deserts are expanding, while rainforests are drying out, all due to a change in the chemical makeup of the air. This blend has always been in flux. We alter the proportions with each breath we take. But our factories and homes, planes and cars, amplify the process. For over 2 centuries, we have been dramatically increasing the amount of warming carbon dioxide in the atmosphere. So far, the planet's natural air filters have pulled nearly 55% of it out of the air.
The North Atlantic has absorbed a tremendous amount of carbon dioxide, but at the moment it's almost completely saturated by carbon dioxide, so it's not absorbing very much more. It's almost like a bottle of some kind of soda pop. If you warm it up a little bit, it'll actually fizz and release CO2.
As these natural safety valves close, we will face an even more dramatic rise in temperatures. The global average could be up 7 degrees Fahrenheit by the end of the century, wreaking havoc with weather patterns and habitats. We can prevent climate change by preserving the air's delicate blend of gases, the unique mix that sets Earth apart. And our planet is also marked by how this blend sits above the surface in a distinct layered structure. As we rise above the clouds and winds of lower altitudes, we enter a completely new zone. A world of extreme temperatures and ever-thinning air. Air that would kill us in seconds, but which shields us from deadly radiation. We live in a tiny sliver of Earth's atmosphere called the troposphere. Winds and clouds, rain and snow dominate this turbulent zone, but above it lie miles of freezing dry air. The conditions there would kill a human in seconds, but we desperately need the high atmosphere's weight and protection. Engineer John Powell's balloon team has spent 27 years exploring its layers, pushing further and further into this remote, dangerous world.
Sometimes we just run into a phenomenon that we have no idea what that was. We just have this moment of data in it that we need to go back and explore. But it really is like a completely alien, foreign world up there.
The team has made over 90 launches. Each one edges them closer to their ultimate goal of reaching space.
You can use balloons not just to go to the edge of space like we do now, but go all the way over the line and actually use balloons or airships to go all the way into space. Space travel without the rocket.
Officially, the atmosphere ends and space begins 62 miles up. This sounds high, but on a tabletop globe, that would only be as thick as the coat of varnish. And in reality, the air extends out much farther. The atmosphere's lowest layer, the troposphere we live in, ends 40,000 feet up, the cruising altitude of airliners. Above are another 4 distinct layers.
They're all separated by their temperature. It gets colder and colder and colder, then it warms up to a nice toasty 0, and then it starts to get colder again. So whenever the temperature changes directions, you know you've made it into another layer.
First comes the stratosphere, a stable layer without strong winds. Then temperatures in the mesosphere plunge to minus 150 degrees Fahrenheit. Above that is the thermosphere, where solar radiation can push the thermometer back up to 4,500 degrees. And finally there is the exosphere, an endless zone where air molecules slowly thin out into the pure vacuum of space.
Now the exosphere is really high. They actually detected particles of the Earth's atmosphere on the far side of the moon during the Apollo program.
As Powell's balloons rise towards space, they leave the world we know far behind. The air thins, and they begin to lose the protective weight of the miles of air above them.
The pressure is dropping. When you finally get to the stratosphere, to the altitude we like to work at, it's only 1/100th that of it is on the ground. It is a whole different world than down here.
The weight of the miles of air above us creates air pressure. We often think of air as weightless, but all those gas molecules add up. Grand Central Station's main concourse contains over 200 tons of air. As gravity pulls the air down, it compresses the layers below, making them denser. This dense air is what we are used to dealing with on the ground. Just a pint of it contains more than 8.5 billion trillion gas molecules. But higher up, around the balloon, there is less atmosphere pressing down from above. The air up here is thinner.
It's like being under 1,000 blankets, and each blanket is a layer of the atmosphere, and we're being pushed under all of these blankets. Now, as you go higher, you're going up through the blankets, so it's pushing on you less, until you're at the top, then above most of the blankets where you don't feel it at all.
That thin air seems alien to us because our bodies and technology are so perfectly adapted to thicker air. We even need it to hear. The gas carries sound through air as pulsing waves of pressure.
Sound is just a wave, like a water wave in a pond. But if you take away the water, there's nothing for the wave to go across. And as the atmosphere gets thinner and thinner, it supports that wave less and less and less.
Finally, in the vacuum of space, there is nothing to carry the wave, and even the largest explosion is silent. We also rely on thick air for propulsion. Propellers work by pushing against it, like a swimmer pushing against water. With so little air resistance to work with, Powell's high-altitude airships have to use a top-secret propeller design to maintain thrust.
When propeller experts and high-altitude experts look at our propeller, they go, oh, that can't possibly work. And then we always show the video of it flying around at altitude working just fine.
Like a champion swimmer, the design gives the propeller maximum possible thrust against the thin air of high altitude. And when the airship reaches almost 20 miles high, it is working against a new backdrop. Gone are the blue sky and white clouds of the troposphere. Instead, the darkness of space dominates the sky.
The sky is completely black, and you actually see the curve of the Earth, and it looks like you're in space aboard the space shuttle. And you see a bright blue and purple line right at the transition of the top of the atmosphere. And it's the only time you can actually visually see the atmospheric layers.
The color change marks the thinning air. At ground level, sunlight passes through miles of air molecules before it reaches our eyes.
It's like going through a prism and breaking it up. And that's why you see the blue. But you take away the air, and even though it's daytime, the sky was black.
School science experiments on board the airship study the dramatic pressure change.
And we call it a PONGSAT, for ping pong ball satellite. And it's real simple. The first thing they do is they have to cut the ping pong ball in half. Then your experiment goes inside. And the simplest and my favorite is where you take like a little mini marshmallow and they just drop it in the ping pong ball. This is satellite construction at its best. And then we take them to the edge of space.
In the thin air of the stratosphere, the marshmallow is no longer held together by high air pressure. Air bubbles inside it expand, causing the spongy candy to bloat outwards and burst open the PONGSAT. Just as the thin air is dangerous for marshmallows, it can also affect flesh and blood. Contrary to popular belief, your blood won't boil. It's held in by your blood vessels. But any exposed flesh will swell out like the marshmallow. And at around 26,000 feet, the air is too thin to breathe. There just aren't enough molecules in every lungful of air. And starved of oxygen, your brain will begin to shut down.
You know, the extreme cold would get you, but the lack of pressure would get you first.
As the balloons rise higher still, they face attack by an invisible bombardment: radiation. Every day the sun radiates a titanic amount of energy, some of it in the form of high-energy ultraviolet rays. These rays pack a powerful punch, and in the high atmosphere, they attack the structure of Powell's balloons.
The UV literally damages the material, and you start getting microscopic cracks in the material, which makes it brittle. You know, eventually it just fails, and the balloon pops.
The rays are potential killers, both for balloon and human. They bombard our cells and DNA, triggering cancers. But around 7 miles up, a layer in our atmosphere shields us from 99% of these rays. It is made up of ozone, a rare molecule of 3 bonded oxygen atoms. This can absorb and block high-energy UV rays.
The ozone layer, it's not like this saran-wrap thick layer, a boundary that you pass through. It's actually miles and miles thick, so it's a slow diminishment.
Man-made chemicals used in refrigerators and aerosols have been eating away at this delicate protective layer. Every winter, holes in the shield appear over the poles. The harmful chemicals are now banned, and the layer is beginning to recover. And above it, the fragile air of the mesosphere is shielding us from another deadly barrage from space. In East Texas, Jeff Notkin and Steve Arnold are searching for the remains of cosmic missiles that have been shattered by our atmosphere. Fragments rarer than diamonds and worth their weight in gold. Meteorites. These two professional hunters seek out space rocks buried in the fields and prairies.
This search for meteorites allows me the chance to touch a little bit of what's from out there, bits of the cosmos that have found their way to us.
The hunt has taken Steve and Jeff from Siberia clear down to Chile, and some of their finds have been spectacular.
The largest meteorite I found was 1,430 pounds. It was a large stony iron meteorite from up in Kansas. we didn't realize was that big of a deal. The media kind of picked it up and ran with it.
He's very modest. It's not only Steve's greatest find, it's one of the greatest finds ever made in meteorites.
The massive space rock has been valued at up to a cool $1 million. But this is a rare find because most meteorites simply don't survive a brush with Earth's atmosphere.
Most of them don't make it to the surface. The atmosphere is our friend in the sense that it protects us from these rocks from space, but for meteorite hunters it's also not our greatest ally because it burns up a lot of what we're looking for.
Steve and Jeff search for remaining fragments using a custom-built metal detector rig.
Meteorites will have iron in them, and it's ferrous, and so not only will a magnet attract to it, but also a metal detector will be able to pick it up.
Every year, over 18,000 meteorites lock onto a collision course with Earth.
When meteorites encounter our atmosphere, they're traveling at the speed that they acquired while moving through the vacuum of space. And typically, they're traveling at many thousands of miles per hour.
As they head down to Earth, they cut through the outer reaches of our atmosphere. But once the meteorites enter the mesosphere, the air starts pushing back.
We can't see the air around us, and we can only feel it on really windy days like this. But a meteorite encountering our atmosphere definitely feels the air, and that is because it's traveling so quickly. When it encounters our atmosphere, the air in front of the meteorite cannot get out of the way in time. It's almost like the meteorite hitting a solid wall, like a block of concrete.
As the air in front of the meteor compresses, it also heats up to more than 30,000 degrees Fahrenheit. Eventually, it bursts into flame, lighting up the sky. When you see a falling meteorite or shooting star, it's actually the protective shield of air that you see burning, not the meteorite itself. But the friction and heat wears away at the space rock. The hot air actually melts the metal surface. And often the collision with the atmosphere, the metal surface. And often the collision with the atmosphere.
This is an actual meteorite, and if this were to encounter the atmosphere at high speed in its current condition, and that's the result.
Only fragments of the original asteroid survived the fall to Earth. Their speed has dropped from 17,000 to 300 miles an hour. Rocks as big as station wagons have shrunk to the size of golf balls. They impact on the surface, forming holes a few inches deep. The chances of finding one are remote.
There we go.
I'll get the shovel.
Right about there, Maestro.
It looks promising, but this time the guys are out of luck.
So yeah, we found a plow, and basically a lot of different types of trash can be in these fields, and so anything that's ferrous, our detector's going to pick up. Meteor wrongs, as we call it, as opposed to a meteorite.
On average, they uncover 75 meteor wrongs for every meteor right.
This is a genuine iron meteorite. This is believed to have once been part of the core of a long-dead planet or asteroid. And this was found right here in this strewn field. These remarkable little shapes, indentations on the surface, are called thumbprints, or scientifically, regmaglyphs. And that's a feature that's unique to meteorites. And these little markings are caused by the surface actually melting as it flew through the atmosphere. We don't find regmaglyphs on Earth rocks.
The air is constantly at work, making meteorites rare and valuable.
The chances of meteorites surviving their journey through the atmosphere and being found are minuscule. If it wasn't for our atmosphere, we would have little particles raining down on us all the time, and some of them not so little.
The mesosphere's barrier of thin air is the final gift from our atmosphere, adding to the oxygen we breathe, water we drink, and pressure we feel. But as we cross into the layers above, we leave life far behind. John Powell's airships have only reached the upper stratosphere. Kittinger's jump point is below that, in the middle of the stratosphere. The only people who travel through the superheated thermosphere and distant exosphere are astronauts heading for space. One day, these manned space missions may reach out even further, to distant planets with alien atmospheres. Atmospheres that may support their own life forms. Life evolved to suit the pressure, chemicals, and structure of that air. And our best chance of finding those alien organisms may be by looking for the right sort of atmosphere.
One way to look for life elsewhere in the universe is to look for an atmosphere that's unusual in the way that Earth's atmosphere is unusual. I mean, Earth's atmosphere really stands out in our solar system. And it's not a coincidence that that unusual atmosphere is on the planet that has the abundant life.
Life releases gases like oxygen that aren't found in most atmospheres. Spot these gases and you might have found alien life. But it's more likely to be little green bugs than little green men.
It's hard to imagine finding other planets where humans could live too easily, but it's easy to imagine finding other planets where bacteria from Earth could live easily. Bacteria are much tougher than us.
Earth once lay under one of these alien, hostile atmospheres. And just as cyanobacteria transformed the atmosphere of Earth, alien life forms could do the same on their planet. And once the atmosphere starts evolving, life can also move forwards, gaining ever more complexity. Joel Hagen has spent 20 years imagining how those atmospheres could have affected their inhabitants.
That's where some of the real creative joy comes from, is trying to think about everything that has happened here and then take yourself one notch beyond it and imagine, what haven't I seen yet? And then try to visualize that.
One of the possibilities that intrigues Hagen is life on a gas giant planet.
This is an environment so completely alien to what we're used to. Even a planet like Jupiter, for instance, has no solid surface, just a gradual transition of densities of gases. And I think we might imagine creatures in an atmosphere like that sort of relied on buoyancy, perhaps being able to generate hydrogen, for example, somehow within their bodies.
These creatures would be like hydrogen-filled blimps, lighter than the air, able to float amongst the gas clouds.
The concept that I have here is to have perhaps colonies of microbes in these sort of tentacle-like structures here. And these microbes generate the hydrogen, which in turn sort of inflates the gas bag here. A creature like this then could sort of float freely at certain levels in the atmosphere.
On other planets, with denser atmospheres, larger, more complex creatures could take to the skies. The thicker air would support them aloft, allowing bulky reptiles to glide and fly.
This creature probably wouldn't be able to fly very well on our planet, but even on a planet like Titan, for instance, that has a surface gravity only about 15% of Earth's, but an atmospheric density at ground level about 1.5 times. Even a person with wings strapped to their arms could fly in an atmosphere like this, so we could have creatures like this.
Hagen bases his ideas on known planets and the evolutionary history of Earth. But it's all pure speculation, until we find life in alien atmospheres.
I would be pretty thrilled just to find microbes under rocks on Mars, for instance. They don't have to walk up and shake hands with me to get my blood up. I would be pretty happy just to know that life has happened twice.
At present, we are alone. Life may have happened just this once. And if it did, then it's only because of our planet's unique atmosphere. As we have soared for miles above the ground, we have journeyed through this ocean of air. The air which shields us, supports us, and sustains us with every breath.